All right, so we've talked about how atoms decide what charge to take, and by decide, obviously, they have no brain. They're trying to get to an octet, though, and so the atoms will gain or lose electrons, which gives them a charge, and they do this to try to get to an octet. Some things are a little bit different, though, and I just wanted to talk about the exceptions that we didn't talk about. On the transition elements, so D block, a lot of those metals have more than one possibility. And so, for instance, copper's sometimes +1 or +2, iron's sometimes +2 or +3. When we have those situations, we actually have to mess with the name. We can't just call it iron because, first of all, it's, we don't know whether it's iron 2 or iron 3. So we put Roman numerals by it. Iron 3 means it's iron with a +3 charge. It doesn't tell you how many of them there are. It just tells you what the charge is. Iron 2 is +2. So then you would have copper 1, copper 2. And this is true for a lot of those transition elements. A couple of them, though, that seem a little sketchy are not. And they actually make a stair step going in the reverse direction from the stair step that's already there. Silver, not copper, okay? Copper is different. We already talked about copper. Silver is always a +1 charge, okay? Silver, always +1. Zinc and cadmium are always a +2. So on the periodic table, it goes like this. And then the aluminum column is always going to be +3. So like aluminum, gallium, and indium, they are like this. So you see how this makes a stair step. And then if you look on the periodic table, it actually goes down the other direction for the semiconductors. So you can always bank on these, that you will never say zinc 2. You just say zinc because it's always a +2. You're never going to say silver 1 because it's always +1. So you just say silver. Same with cadmium and aluminum and gallium and indium. Group 13 typically forms a +3 charge. 14 could be a +4, -4, but a lot of times they're going to bond covalently. They could even form a +2, but we might talk about that later. Anions, we've already talked about all this. There's nothing really too crazy about anions. A little bit of terminology, though. A monatomic ion means one atom with a charge. If you see polyatomic ion, that's multiple atoms with a charge overall. So that's a good term to know. And here's a little chart, kind of shows you the trends, I guess, on the charge. So we got to talk about compounds. An ionic compound is composed of cations and anions. If you only have 2 elements involved, then we call that a binary ionic compound. 2 elements involved, not 2 atoms, but 2 elements involved. Chemical formula, obviously, we've already talked about this. It's going to show the kinds and numbers of atoms. A formula unit is the lowest whole number ratio. It's like a molecule, but for ionic compounds. So, 2 element compounds that form between monatomic ions. Here, to form these, all you have to do is cancel the charge. So if you have sodium, that's a +1. You can pick anything with a -1 and it'll match up. Chlorine here has a -1, so we put NaCl. Magnesium has a 2+, and you can put anything with it as long as it cancels the charge. Bromine has only a -1, so you actually have to have 2 bromines to cancel. So you have to have a neutral one to make an ionic compound. But both of those, like I said, are binary ionic compounds because they both only have 2 elements. So aluminum bromide, even though it has 4 atoms, is actually a binary ionic compound because it has 2 elements. Aluminum is +3, so you have to have 3 -1 bromines in order to cancel it out and make it neutral. Okay, we've already talked about this. When you are writing formulas for binary ionic compounds, the cation, the positive part, is always first. Charges have to add up to equal 0, and you do not write any of the charges in the final formula. To do this, you just find the least common multiple of the charges and make sure they cancel out. So, for instance, aluminum chloride, aluminum's +3, chlorine's -1, so this would be the formula. Lead 4 oxide, lead 4 meaning it's lead with a +4 charge, so you have to have 2 oxygens, because each of them are -2, to cancel this out, so you got PbO2. We've already talked about the properties of ionic compounds, so I'm going to skip. That's funny, it's off on the thing. Sorry, I'm kind of going fast. With metallic bonding, we didn't talk about this, okay? Metallic bonding involves a sea of electrons. Metals kind of share their electrons like a commune. They don't, see, oh, this is mine, this is yours. They kind of just share it. And so they're just free-flowing. This is why metals can conduct electricity, because we can pump in electrons from one side and they will flow out from the other, because the metals just hold on to their electrons really loosely. They're all free-flowing. So metallic bonding helps explain some of the properties. They're ductile, so they can be drawn into wires. We can hammer it out into sheets. They're malleable. This is because they don't have this really strong crystal structure. See, if we shove this down, the like charges are going to be by each other and they're going to break. Whereas with the metals, it's just a sea of electrons, so it just kind of, does whatever. It goes with the flow. Alloys are mixtures of metals. This is what we made when we did the gold penny lab. We made an alloy. This is some of the makeup of alloys. We've already talked about this, so I'm just kind of going fast. That is the end. So the main thing to remember here is with your naming and writing of binary ionic compounds, you always just say the first atom first, the name of the first atom, and then you say the name of the second atom with the IDE ending. The negative part always gets an IDE ending, notice. Okay, so if you know you have lead and oxygen, first thing you got to do, since it's lead, you don't know the charge, you got to figure out the charge. Well, oxygen's always -2. If each oxygen's -2, that means you got a total of -4. Lead would have to be +4, so lead 4, just say the Roman numeral like a number, and then oxide, because it's an anion.